Hi everyone, my name is Teja and welcome to this probability refresher for business analytics and machine learning video series. In this video, we're going to continue looking at um, multiple random variables. So in particular, we're going to look at conditioning with other random variables. So RVs is a short form for random variables. And then I'll get to the notion of independence as well. So we saw conditioning with conditioning a random variable with respect to an event before. So we saw probability of x given a. So now what I'm going to do is I'm going to talk about probability of x given another random variable. Let's say y is equal to y. Let's say now. By the way, when I write this, it looks like I'm not specifying what value x little x, which is the random variable, takes, but this is just a short form for probability of x is equal to x given a for every little x. So I didn't want to expand this out, so I just wrote this as the conditional probability law. Okay, so notice that actually, if you think about it, this conditioning on another random variable is not that different from conditioning on an event, because we just saw that because probability of y is equal to little y, this is the same as looking at this event omega in omega. So this notation just means in, okay, omega and omega, such that y, which is the function of outcomes, y of omega is equal to little y. Okay, so let's think of this as an event. In fact, let's think of this as event a. Then this just boils down to the discussion that we had of conditioning a random variable with respect to an event. So this is great. Then what we can actually do is we can also do, remember when we had events probability of a1 intersection a2 intersection a3, sorry, a3, we were able to do probability of a1 times probability of a2 intersection a3 given a1 times probability of, this is it, which we can further write as probability of a1 times probability of a2 given a1 times probability of a3 given a2 and a1. Okay, so we said that this we can actually factorize this probability into a product of three conditional probabilities. Similarly, we can do the same thing with random variables. So probability of x is equal to x, y is equal to little y, and z is equal to little z. We can break it down as probability of x is equal to little x times probability of y is equal to little y given x is equal to little x times probability of z is equal to little z given y is equal to little y and x is equal to little x. Okay, so this is something that you should practice, and this is a this is going to be very useful. These types of factorizations or expanding multiplication rule is very useful in what I keep referring to as graphical models, which include Bayesian networks or Markov networks, and basically undirected and directed graphical models. So this is the notion of conditioning over other random variables. Notice that it's kind of not, you don't really have to always think of the underlying sample space when you talk about random variables. You should be comfortable with just talking about random variables and their probability laws directly, and if needed, you can always check whether these probability laws and the random variables, what are the actual outcomes in the sample space that these guys correspond to. Okay, so that's that. So now let's look at the notion of independence. We saw independence of events, so now we're going to look at independence of random variables. So let's say two random variables x and y are independent if, this is the definition, two random variables are independent if the probability of x is equal to little x and y is equal to little y should be equal to probability of x is equal to little x times the probability of y is equal to little y. And if you interpret x is equal to little x and y is equal to little y as events, then this should be straightforward based on what we have already discussed. A consequence of this is that if you have a function, let's say g of x of y, it's a function of x and y. Let's say the function is x times y. Okay, if the function is like this, then the expectation of g of x comma y is going to be what? It's just the expectation of x times y. And if the random variables are independent, you can actually, it turns out that you can just write it as expectation of x times expectation of y. And you don't have to believe me blindly. We can actually do it in one line. So expectation of x times y is nothing but sum over x sum over y of x times y of probability of x is equal to x and y is equal to y. And this we know was just splits into two things here. So we can just write it as sum over x sum over y, x times probability of x is equal to x. And you can also see y times probability of y is equal to y. Okay, so this is nothing but you can, this doesn't depend on y, so you can write it as sum over x of x times p of x is equal to x times sum over y of y times p of y is equal to y. And this is what the individual expectations are. So we just showed that. Now think of another function. So this time g of x comma y should be, let's say it is equal to x plus y. Then it has consequences for even the variance as well. So remember, what is the variance? Variance of g of x comma y, right? So this is g of x comma y is a derived random variable because it's a function of a bunch of random variables. Now variance of g of x comma y in this case is the variance of x plus y. It turns out that the variance of x plus y, if x and y are independent, is just the variance of x plus variance of y. I'm not gonna show this, work this out, because it is essentially very similar to the way we did this. We just use this we just use the definition of independence here, and in particular, we're really not doing very different from what we did with events, except that we're using a new notation, which is the notation with respect to random variables directly, and not really thinking about the underlying sample space. We are not directly thinking about the underlying sample space and the outcome space and the bunch of outcomes or events, elements. So that's it for this video. Thank you for watching.